Hi. So in this video we will start talking about quantum models of computation and quantum complexity classes. So models of computation are mathematical abstract devices that study the limits of computability. And we saw earlier that circuit models were used to define quantum algorithms. But those are not the only way to construct quantum algorithms. We could also use abstract models of computation, but in fact, they define the same class of functions. The circuit approach and abstract models of computation, they practically define the same class of computable functions. But it's more easier to define algorithms by using the circuit model. But this is also an alternative approach to define algorithms using models of computation. So for this we need to define a standard model. We need to have a standard model of computation, and classically this is known as a Turing machine. Okay? A Turing machine is a universally accepted standard model of computation. And since we are mostly interested in quantum algorithms, we need to define the quantum counterpart of Turing machines. Now, quantum Turing machines have their own advantages and disadvantages over the circuit model. One advantage of the circuit model is its convenience. So it's more easy, more intuitive to construct a quantum algorithm by using circuit models. But one advantage of using models of computation, quantum Turing machines in particular, is that the input size is that we can define any quantum algorithm regardless of its input size. Because for quantum circuit models, the size of the circuit input wires depends on the size depends on the input size of the argument. So quantum Turing machines in that aspect are more general. They allow us to define any quantum algorithm regardless of the input size. Okay, but on the other hand, we need to have specific circuit models. We need to define specific circuit models for specific quantum algorithms. Okay. All right. So we want to define the quantum counterpart of the quantum counterpart of Turing machines. But before that, let me review some notions in formal language theory. Okay, so an alphabet is basically a finite set of symbols. Okay, alphabet. So this is a finite set of symbols. And using a finite alphabet, we define strings over the alphabets. By string, I mean sequence of symbols. And a set of strings is called a language. So language is just a set of strings over some alphabets. Okay? Or we call it a formal language. Okay, so for two given strings, if W and U are two strings, then WU simply denotes the concatenation of W and U. And we also denote the length of W by this notation, length of U. Length of U means the size of W. It's the number of characters contained in W. There's a unique string of length 0, which is called the empty string. We denote this by lambda, empty string. So empty string is of length 0. Okay? And for any W lambda is equal to lambda W, and that's equal to W. Okay, so if sigma is an alphabet, then sigma to the k denotes the set of all strings of length k. Okay. And sigma star denotes the set of all strings of any length over the alphabet sigma. And sigma star also includes the empty string lambda. Okay. Okay, so a Turing machine is an abstract model of computation, which was first introduced by British mathematician Alan Turing in the late 1930s. It's a universal model of computation, and it models, it corresponds to the abstract counterpart of digital computers. So a deterministic Turing machine, let's define what a Turing machine is. A deterministic Turing machine or simply Turing machine, is a six-tuple containing Q, sigma, delta, Q0, QA, QR. Okay, so where Q is the set of finite states, sigma is the alphabet, delta is the transition function defined as, so it gets a state, it gets a symbol from the alphabet, it maps to another state, another symbol in the alphabet, and left stationary or right movement of the tape head. Q0 is an element of Q, QA is simply, again, an element of Q, and so is QR. Q0 is the initial state of the machine, QA is the accepting state, and QR is the rejecting state. Alright, so let me draw the picture to understand this intuitively more better. So a Turing machine essentially consists of an infinite tape divided into cells on which we can write some symbols from the alphabet. So if our alphabet consists of the symbols 0 and 1, we could write symbols like 0, 1, 0, 1, and so forth. So it consists of an infinite tape divided into cells. It also contains a tape head, a head which reads and writes symbols on each of the tape cells. The tape head can do left-right movements, or it can stay stationary. Now, the reason that we call this machine deterministic is due to the definition of the transition function delta. Now, for each Q times sigma, we have a unique mapping. Okay, it doesn't map to two distinct elements. It just maps to one unique element. Okay. Later on, we will see the non-deterministic Turing machines. We will define them later on. But right now, we are working with deterministic Turing machines. So a configuration of a Turing machine consists of the information which contains the state of the machine, so a configuration of a Turing machine contains the information of the state, current state of the machine, the tape content, and the tape position on the tape head. That is the next symbol that is to be read. Okay. So it's a triplet consisting of Q, X, Y. Okay. So Q here is an element of capital Q. X is an element of sigma star, and so is Y. So how does the computation, how is it carried? Okay, so we start with the initial state. Okay, the machine starts in its initial state. The input is written on the tape head, and the machine starts by reading the first symbol, the leftmost symbol of the input, and the computation is carried according to the transition function, basically. Okay, so each rule determines a step of the computation. Now, to understand this better, let's decompose the content of the configuration. So, okay. Now, if our configuration looks something like Q, X, Y, okay, and suppose that the first symbol of Y is A, so A, let's suppose that is the first symbol of Y, then we can write this as Q, X, A, W. Okay, so A, W equals Y. Now, at this stage, the machine is in state Q, okay, the tape content is X, A, W, and the next symbol that the machine will read is A. So A is the symbol to be read. And depending on the definition of the transition function, okay, so we're looking at the transition when in state Q we are reading symbol A. Okay, so let's say that it maps to P B and let's say it goes to the tape head moves to right. So in this case, if we are in this configuration, then the next configuration will be, so the machine will be in state P, okay. The tape content will be so A will be replaced by B, okay. And then we move one step left, okay. One position right. Sorry, this should be, okay, B should be here because we're moving right. And then we have W. So this is the next configuration, C1, C2. We delete A and we rewrite, in place of A, we write B, and then we move one step right on the tape heads. And the next symbol that we read will be the first symbol of W. Okay. All right, so if we are in configuration C, and if delta yields C prime, then we say simply that C yields C prime. Okay, and this is denoted by C prime. So in this case, from C1, we obtained C2. Okay, so each yield defines a computational step. Okay. All right, so there are two exceptions, though. These two exceptions are when we are at either of the end of the inputs. Okay, so if the so we know that the length of the input is finite. There are two exceptions. One is that if we are on the end of the input, so suppose that we are on state Q1, we have W and lambda. So this means that we finished reading all the symbols of the input. Okay, we're at the end of the input. And secondly, next exception is Q1 lambda W. Okay. But we can overcome these exceptions by adding a blank symbol in the tape alphabet. And then we could extend the definition of the transition function by replacing Q1 W lambda with Q1 W hashtag, and replace also similarly Q1 lambda W with Q1 hashtag W. Okay, so it's no problem. Now, if at any point we end up being in state Q alpha, okay, then we say that the computation is accepted. Okay, the input is accepted. So being in QA means that the computation halts in an accepting state, and in this case the input is accepted by the Turing machine. If, however, we end up being in state QR, that means, so the computation still halts at this stage, but the input is rejected. And the computation goes on indefinitely, unless we end up in either of these states. Okay. All right. So let me give one example. So suppose that our alphabet is sigma 0, 1. Okay, so let's try to find if the input, if the given input contains the symbol 1. So let's design a Turing machine which decides if the given input contains the symbol 1. It contains symbol 1 anywhere in the input. Okay. Alright, so let's suppose for convenience that we start reading from the midsection of the input. Okay, normally we start reading from the left-hand side, but in this case, let's assume that we start reading from the midsection. So if we come across with any 1 in the input, then the machine will go into the accepting state and the computation will halt. If there is no 1 in the input, then after reading all the symbols, the machine will go into the rejecting state. Okay. All right. So let's define the set of finite states Q. Let's say Qi, Q initial. Another state would be QL, QR, QA, QR. It will become clear why we define Q in this way. Alright, so and then we define the transition function delta in the following way. Let me actually draw a table. Okay, so let's suppose that the columns represent the symbol that we are reading. So if we read 0, 1, and if we read hashtag, and let's suppose that the rows represent the current state of the machine. So if we are in state QI, and if we are reading 0, then the machine will go in state QL, and then we move the tapet one step left. If we read 1, in any case, the machine will go in state Q accept. Okay. If we read the hashtag symbol, so that hashtag symbol denotes the end of the input, okay, then that means, well, we haven't come across anyone, so we need to reject the input, rejecting state. Okay, so if we are in state QL, if we read 0, then we will be in the same state, and we keep going to the left. If we read 1, then we stop and we accept the input. If we read the end marker as we go left, then we need to stop, and then we need to go left and read the symbols on the right. Okay. So we change our state to QR, and then we move the tape head to the right. Now, if we are in state QR, that means if the machine was continuously moving its tape head to the right. Okay, so if we are reading the right-hand side of the midsection of the input, if we read 0, then we keep going to the right, so we'll be in state QR and keep moving right. If we read 1 at any stage, then we accept the input. And if we end up reading the end marker, we reject the input. That means we read every symbol without coming across any 1. Alright, so this Turing machine decides whether a given input contains the symbol 1. Okay. Alright. Now let's make a note here. Just because a machine being in the same state doesn't mean that it's in a loop. So being in a loop means something different. So how do we understand if a machine is in a loop, theoretically speaking? Well, if the machine is in a loop, then that means we have the same configuration at distinct stages. So that's the definition of loop. Okay, being in the same state, on the other hand, doesn't mean that the machine is in an infinite loop. Okay, but being in the same configuration at distinct stages means that the machine is in a loop. All right, so Turing machines actually model the intuitive notion of algorithms. Okay, so for that reason, Turing machines might not halt, might not terminate on any given argument, on any given input. So the computation might continue forever. But a Turing machine can also be thought of as an enumerator. An enumerator in the sense that it could enumerate the strings that it accepts. Okay, so it could also be in the role of an enumerator. And if L is a language, so let's define what it means for a set to be recursively enumerable. Okay, so we let L be a language, a set of strings basically, be a language, and let T be a Turing machine. Okay, so if T accepts W, when W is in L, but if there is no guarantee that the Turing machine T rejects W when W is not in L, Okay. Then L is called recursively enumerable. Okay. So the Turing machine in this case decides only one way. If the input is really in L, if W is in L, okay, then T will accept W, but if W is not in L, T may not reject W. Okay, the computation might continue indefinitely. Okay, but on the other hand, L is said to be recursive, or L is said to be decidable. L is decidable if V is accepted if and only if is accepted by T, if and only if W is in L. Okay. L is decidable if W is accepted by T, if and only if W is in L. So it decides both ways. So in this case, L is called a decidable set, a recursive set, okay, or a computable set. Okay, they all mean the same thing. Intuitively, computable set means that we can always decide by a Turing machine whether a given element is in that set or not. Okay, but if we only decide one way, then it's recursively enumerable, or it's semi-decidable. Okay, and think of a recursive enumerable set in the following manner. Something is a set is semi-decidable or recursively enumerable if we can only decide one way. So if that element is in the set, if the given element is really in the set, then we can always decide. Then there's always a Turing machine that decides that. But if the element is not in the set, then there's no guarantee that the Turing machine will halt and reject that input. Okay, so this is what semi-decidable means. So then, by definition, any decidable set is semi-decidable, right? So any recursive set is recursively enumerable. So let's actually denote these classes by R and RE. So let R denote the class of recursive sets, and let RE denote the class of recursively enumerable sets. So it's easy to see that by definition, any recursive set is a recursively enumerable set. Okay? But not vice versa. So not every recursively enumerable set is recursive. And this is due to the famous halting problem. A halting problem is the problem whether or not a given algorithm halts on a given input. Okay, so we're given an algorithm and we are given an input for that algorithm. So we want to decide whether that algorithm will halt on the given input. And there's no algorithm that decides this problem. Okay, there can be no algorithm that decides the halting problem. Um, but the set that encodes the halting problem is recursively enumerable. Okay, I'm not going to explain it here, but the details are in the lecture notes. The set encoded by the halting problem is recursively enumerable but not recursive. So there are sets that are recursively enumerable but not recursive. For example, the halting set. Okay. More specifically, the set and the index set, which is defined as k equals I, such that the ith Turing machine halts on input I. Now, Turing machine descriptions are finite, okay, so essentially they can be seen as algorithms. So we can uniformly enumerate all possible Turing machine definitions. Okay, the first Turing machine, second Turing machine, third Turing machines, and so on. We can have a uniform enumeration of all Turing machines. And when we do that, we can define this index set K, the halting set. And K is turned out to be recursive, but not. It's turned out to be recursively enumerable, but not recursive. Okay. All right. So now Turing machines really model our intuitive, the intuitive notion of effective computability. But this is not a mathematical statement. It relies on a philosophical thesis called the Church-Turing thesis. Church-Turing thesis. The Church-Turing thesis states that Turing computability equals intuitive notion of effective computability. So we can't really formally define what effective computability is, but we believe that it's equal to Turing's definition of computability, computation by Turing machines. So if a function is effectively computable, then it's also Turing computable, okay, and vice versa. And this is called the Church-Turing thesis. It's a philosophical statement because we can't formally prove it. Okay, there's no way to formally prove it. There may be arguments that adhere for the Church-Turing thesis, or supporting arguments, convincing arguments. But there can be no formal proof because there's no formal definition of effective computability. On the other hand, Turing machines are formal mathematical models, and they are well defined. Now, you might be wondering, well, aren't all functions computable? Well, the answer is negative because, as a matter of fact, Turing machines are defined from a set of natural numbers. They're defined from the natural number domain to the natural number domain. Okay, so the input to Turing machines are finite strings, right? An algorithm takes as an input a finite string. So we can have a one-to-one bijection between finite strings and natural numbers. So Turing machines are defined from natural numbers to natural numbers. The input is a natural number, a finite string, and the output is another finite string. or another natural number. There's a one-to-one correspondence between set of natural numbers and set of finite strings. So classical computation lies in the domain of natural numbers. Okay, but how many functions are there from n to n? Well, there are n over n many functions. Okay. But how many Turing machines are there? Well, we have an enumeration. Since we can enumerate all possible Turing machines, there's a bijection between the set of all Turing machines and the set of natural numbers. So there are only countably many Turing machines. But n to the n is uncountable, so there are uncountably many functions from n to n. In other words, there are uncountably many problems, but there are only countably many algorithms. So that means that there are only countably many decidable sets, but uncountably many undecidable sets. Or there are only countably many computable functions and there are uncountably many uncomputable functions. So almost any function that we see, almost any set that we take is uncomputable. Okay, but we are not concerned with uncomputable functions or undecidable sets. We'll be mostly concerned with the complexity classification of decidable sets. Okay, and we will speak about this later on. So I'll see you in the next video.